Okay, so today's lesson is derivatives. Derivatives is just another very fancy word for slope at a point. We're going to look at some different notations, but essentially the math and the technique behind it is what we have already been doing. So most of the time we have seen limits of this form. This is what we just did as our warm-up question today as well. We use limits to find the slope of a tangent to a curve when computing velocities or any other form of rate of change. When we talk about the derivative, we are looking at the derivative of a function f at a number a, so at a point of interest of a whatever given function. The new notation that we are using is f prime at a. Okay, and if the limit gives us a new function g of x or a number, a finite number, then we know that the limit exists and we know what the slope is. So if we have a line, then the slope of the line is going to be a number, right? Because that's going to give us our y equals mx plus b. If we have a higher order function like an x squared or x cubed, we are going to get new functions that are lower in order, lower in degree. Okay, so sometimes our slope is going to be a new function, not necessarily a number. An alternative way of writing this, we saw this a couple of lessons ago. We can look at a general x away from a general point of interest A, or we can look at a small distance h away from a point of interest A. Either one of these work. They all mean the same thing. This is just a new notation. So if we go back to all the different ways we've been looking at this, y2 minus y1 over x2 minus x1. This is what we learned in grade 9 and 10 and whatever. This represents the slope of the tangent. The slope of the tangent is the limit as h goes to 0 of the function at da da da. I'm basically writing that in here. This also can be represented as f prime. F prime of a is the slope, is the tangent, etc. Okay, so this is just a new notation, but it means the same thing. So here's example 1. If the function is 2x squared minus 5x plus 6, find the derivative at the point of 4, right? F prime at 4. So when we do something like this, we need to find the limits first, the general one, then sub the value. Ooh, good question. Did we start recording? We did. Hooray. Thank you for reminding me though. Okay, so we can do this. We can say the limit as x approaches 4. So I'm going to use this method here. The limit as x approaches 4 of the function 2x squared minus 5x plus 6 minus the function evaluated at 4. 4 squared minus 5, 4 plus 6 all over x minus 4. This part, hopefully you can kind of do in your head or throw into a calculator. Right? We can simplify and collect like terms. This will be 16 times 2. This is 32. This is 20. Yeah. Oh, ooh, yes. Thank you. Minus 2x squared plus 5x minus 6. Great catch. Absolutely. We need to distribute that. Okay. Plus 6 minus 6, that goes away. Negative 32 plus 20. 2x squared minus 5x minus 12. Perfect. over x minus 4. I have a quadratic in the top, so let's factor that. So two numbers that multiply to negative 24 but add to negative 5. Negative 24 and negative 5. 8 and 3. Negative 8, positive 3. I have a leading coefficient of 2, so I need to divide those two terms by 2. So this gives me x minus 4 and 2x plus 3 as my factors. Okay, that's wonderful because now I have a common factor that I can just delete here. And I shouldn't be writing equal signs here. I should be writing limit as x approaches 4. The limit as x approaches 4. Now, because we have it simplified to an equation with no denominator, therefore no violations, I could use direct substitution because I don't have to worry about a denominator. So this is going to equal, that's where my equal sign goes, 2 times 4 plus 3. So my slope is 11. Okay. So that's using this method here. If you have a point of interest, you know what it is. You can use a general X and an A. Let's take a look at another example here. Interpretations of a derivative. We can look at it as the slope of the tangent. So the tangent line to the function at a specific point of interest, and we usually call that point P, is the line that touches this, whose slope is equal to the derivative. Again, this is just a reiteration of what we've already talked about. Okay, so now in example 2, we are given a new function, f of x equals x cubed minus 3x. Okay, I now want to find the general equation at any point. So rather than using the version that we did in example 1, I'm going to use the other version because I want to be able to do it in general terms. This requires a specific point. This I could do in general form. Okay, it's just slightly easier. Okay, so we're looking at the limit as h goes to 0. You could use either, by the way. I just find this one easier when it comes to the general form. Okay, so f plus h, or a plus h, or point of interest plus h. So let's take a look. I'm going to have x plus h all cubed minus 3 times x plus h minus x cubed plus 3x all over h. And now I'm going to expand the top. I'm going to use Pascal's triangle. This is going to be x cubed plus 3 x squared h. So the degrees of x are going down, the degrees of h are going up. 3x h squared plus h cubed minus 3x plus h minus x cubed plus 3x all over h. Things get very ugly very quickly, but then they simplify down to nice little cute equations. So x3 gone. Minus 3x plus 3x gone. Everything else has an h in it, so I can reduce by a degree of 1. Say that again, sorry. Here, this one. Yes, this should be negative. Okay, where?
Oh,
Sorry.
yeah, 3, it should be 3h. Because you're distributing -3 to h.
Oh, yes, negative 3h. See, this is why I keep you guys around. Negative 3 hits both of those terms. Yes. Okay, let's reduce everything that has an h by 1 degree. I think I've done it. So the limit as h goes to 0, what's left? 3x squared plus 3xh plus h squared minus 3.
So the h's go to 0, right?
Now I do the limit, so I let them go to 0 using direct substitution because I've eliminated my restriction. So this means that f prime at any given point is 3x squared minus 3. So the slope to the curve at any given point is 3x squared minus 3. Then it says, determine what is the slope of the tangent at these 4 points. Well, now I can just do a quick table of values, x and f prime of x. If x is 1, 2, 3, 4, I can pretty much do this in my head, right? If I put a 1 there, 3 minus 3, that's 0. If I put a 2 there, that's 2 squared is 4, 12 minus 3 is 9. If I put a 3, what's that? 27 minus 3, that's 24. Now it's getting trickier. 16 times 3 is what? Mental math. 48 minus 3? 45. Beautiful. Okay, so now we know the slope at each of those points. Okay, so this represents the slope of the tangent line at f of x, whatever the key points I need. Okay, let's kick it up a notch. Example 3.
No. No.
Pardon? Okay. We want to evaluate this where x is 0. So let's take the general limit again. The limit as h goes to 0 of 2 to the x plus h now is in the exponent, because that's where my function is, minus 2 to the x all over h. Boo. What do I do here? Okay, that's a good idea. 2x times 2h. So that was a great suggestion. However, I still have an h in my denominator. We could. Okay, let's try the other method. What if we use a general x approaches a, but now instead of x approaches a, I'm going to use the actual point I have. X approaches 0 because that's my point of interest. What happens if we do this method? I get 2 to the x minus 2 to the 0 over x minus 0. Is that better?
Just gonna get 2 raised to power x minus 1 over x.
Mm-hmm.
Still going to with 0 in the denominator.
0 in the denominator, hey? Okay.
If we get, yeah, if we get.
Wah, wah, wah. This isn't working. Let's use a different method. You don't have to erase, just add to the pile here. You look at, if you want to, you can. What is it when we have 2 to the x minus 1 over x? And our point of interest is that x is 0. So let's use a table of values, 0.1, 0.01, 0.001, negative 0.001, negative 0.01. Sometimes we just got to try something new. Okay, I don't have my graphing calculator on my screen, but can you guys grab your graphing calculators? Here is the limit. Okay, that's going to be your y function. And we want to test points close to the point of interest because we cannot simplify our equation very well by hand. Can you tell me what numbers do you get? So this is going to be into your y1, and then you're going to go to table and test some of these table of values. Tell me if what I'm writing matches what you see, because obviously I've been making mistakes already today. Don't trust me. Oops. Already made a mistake. There's 6, 9, 2, 1. Something like that. Are we both approaching this number? And is it a positive number that you are getting? Okay. So we are saying that the limit as x approaches a, 2 to the x minus 1 over x, or x approaches 0, sorry. My point of interest is 0, is going to be about 0.693. So if all else fails, table of values. Okay, this also represents the derivative at 0 equals that number as well. Okay, so we have lots of different methods that we've learned in this unit. Pick one that you're comfortable with, and if it doesn't work, try another one. Okay? Rate of change is another way we have described our limits. So a derivative could be the instantaneous rate of change of a function at a particular point. And this part is really important. It's an instantaneous rate of change, not an average rate of change. So I think we did an example very similar to this in one of our previous lessons. The position of a particle is given by 1 over 1 plus t, where t is a measure in seconds and s is the measure in meters. And we want to find the instantaneous velocity after 2 seconds. So essentially, we want to find v of 2, which is the same thing as s prime at 2. Right? So let's try our function here. The limit as h approaches 0 of 1 over, let's see, 2 plus t. Did I do that wrong?
So that's 1 plus t in the function.
1 plus t plus h, right? That's what we're looking for. 1 plus t plus h minus 1 over 1 plus t all over h. Oh, I remember why I did that. What's our t value that we are interested in? 2. So I had substituted t in my head, that's why. 1 over 1 plus 2 plus h minus 1 over 1 plus 2 all over h. And I'm doing this because I know the question is only asking at one specific point. If it was asking me find the velocity at all these different points, then I would do the general one and then substitute one at a time. But here it's just asking for 1 point, so let's just do 1 point. It'll make a math a little bit easier. So this is the limit as h approaches 0 of 1 over 3 plus h minus 1 over 3 all over h. I have a stacked fraction, so let us multiply 3 plus h, 3 plus h. I'm going to move over here. This gives me 3 minus h all over h times 3 plus h. All right, so I distributed the negative, multiplied top and bottom. My 3's at the top cancel, my h also cancel. So the limit as h goes to 0 is going to give me negative 1 over 3 times 3 plus h. Now, if I let h go to 0, it doesn't violate any restrictions. So I'm going to take the limit using direct substitution. So then my velocity, instantaneous velocity at 2 seconds is negative 1 over 9 meters per second. Questions, comments, concerns? Okay, let's do one more. Yes. Okay, do we know the difference?
But the
Right. Speed is just the absolute value of the velocity. Velocity is speed plus direction. All right. Scrolling through. This is a word problem, your favorite. A manufacturer produces bolts of fabric with a fixed width. Do you guys know what a bolt is?
Pardon?
It's like a roll. If you've ever been to like Fabricland or like end of the roll for carpets, all of it is rolled up into these giant rolls, right? So the width of the roll is the same, but the length is rolled into itself. So the length could be as long as you like, but the width is set. Think of like toilet paper, right? The width of the toilet paper is the same, but the length depends how much you pull out. Okay, so a bolt of fabric with a fixed width. The cost of producing X yards of the fabric is the following function, C of f of x, or C of f of x. Nope, I said that wrong again. C equals, thank you, f of x. So we're not told the specifics, but we are told to interpret what we are looking at. The cost is a function that depends on X, which is the yards of fabric you are either making or buying or whatever. So what is the meaning of f prime of x? The rate of change, right? Primes are a rate of change. what is changing here? Okay, with respect to the yards. So f prime of x is the difference in cost over the difference in yards. So this is essentially the dollars per yard of fabric. So the differentiation will give you the cost per yard. However, we are not told that this is a linear function. So f of x will be the cost of yards at x amount. This will give you the instantaneous cost, because we don't know that this is a linear function. It could fluctuate. If it was a linear function, then the cost of production would look like this. But we don't know that. Most likely, there is some kind of operating cost, right? And if you only make a little bit, you're losing money. If you make a little bit more, and the more you make, right? If you think of like buying in bulk or producing in bulk, right? It could fluctuate. It depends on how much you make. So we can't say anything is specific other than it's the instantaneous rates of change, dollars per yard for a given number of yards that you are either creating or producing. What else can we say about this function? In practical terms, if f prime at 1,000 equals 9, in English terms, what are we describing here? Yes, if you make 1,000 yards, then the rate of change is $9 per yard. That means it's going to cost you $9 to make 1,001 yard, the instantaneous for the next section. But once we make 1,001 yards, we have to do a new derivative. We need to find f prime at 1,001 to see what's going to cost to make the next one, right? Because again, we're thinking about a curve. It's not the same cost no matter what you produce. Okay, which do you think is greater? The derivative at 5,500, 5,500 or 5,000? This is a discussion question. This is an open-ended discussion question, meaning your reasoning should match your answer rather than the answer being right or wrong. So, thoughts? F prime at 50 compared to F prime at 500 compared to F prime at 5,000. If I'm comparing these two, I'm asking you, what is greater? The cost of producing 50 plus 1 or the cost of producing 500 plus 1? What do you think the answer is? Why do you think 500 is greater than 50? Why? Yes. So think of the rate of change. What does it represent? The cost to make an additional yard once you have created 50. Is it going to cost you more to make 51 once you've created 50, or is it going to cost you more to make 501 once you've already made 500? Discuss why. Buying in bulk. So you think what? 500? You think 501 is going to be less money respective to the money you've already spent?
Okay,
Yes.
okay, never mind then.
Yes. Okay, so that's a great point. When we are looking at rates of change, it is respective to the money you've already spent. How much is it going to take you to do the next step, to make the next yard? That's an excellent point. Let's write that in. This is with respect to the money you already spent. So you guys are saying that comparing these two, making the 501st yard will cost less than the 51st because of bulk production, which is a valid reason for your answer. You could make an argument for the other way, but I'm not going to tell you because, again, this is open-ended. I want you to think about it. Okay, now let's compare the other two. If we're comparing making 500 yards, how much will it cost us to make the 501st yard versus the 5,000th and first yard? You think 5,000 would be less for the same argument. Okay, I want you to think of what argument could you make so that it costs less to make the 501st than the 5,000th. What argument could I use to say that the 500 rate of change is less than the 5,000 rate of change? I don't have a limiting factor, so I can't say that 5,000 is the most I can make. Armand? I'm not worried about the total price because I'm looking at rate of change. Okay, think of you guys starting a business from your garage. You can make it to 50, you can make it to 500. What happens if you get an order that places 5,000 units? Can you do it out of your garage? No. So what happens at the 5,000 mark? I could make the argument, could argue, yeah, not enough resource. Therefore, I need to upscale my production. Right? So I could say, all right, I can handle a bulk order of 500, but now if I do 5,000, I need to upscale my factory. So you could make an argument either way, but you got to make sure that your argument matches up with what your answer is. Does that make sense? Okay, that's all for the lesson today.